Hey everyone, so today's notes are titled Solving Polynomials, and we will be using something called the rational zero theorem to help us in solving these polynomials. Now, the rational zero theorem is used to determine all possible rational zeros of a polynomial function. Okay, and essentially the rational zero theorem, we will be using this idea of P over Q, where P are equal to the factors of the constant term, and Q are the factors of the leading coefficient. Okay, so that's the ratio that we use to determine the all possible rational zeros of a polynomial. Okay, so let's go straight into an example. Let's say that I give you the polynomial x cubed plus 3x squared minus 6x minus 8. Okay, we're going to start off pretty easy. And what I want you to go ahead and do is first we're going to list out all the possible rational zeros, and then we're going to find out the actual zeros. And remember, the zeros are another word for the solutions, which are another word of x-intercepts. And you remember, like when we're working with quadratics, you guys know how to solve for zeros of a quadratic, right? You can use a quadratic formula. You can use factoring, you can use completing the square. There's ways to solve for zeros of a quadratic. However, once we're working with polynomials that are no longer quadratics, like for example this one that's a cubic, we can try some of the other factoring strategies that I've taught you guys, like factoring out of a GCF or solving by grouping, factoring by grouping, or things like that. But sometimes it doesn't really work. So this rational zero theorem is a way to factor and to solve for the zeros of a polynomial when methods like that don't work. So the way that you're going to do this is you first need to list out what are the possible rational zeros of this polynomial. Now, the way that you do that, again, is P over Q, which is going to be equivalent to the factors of the constant over the factors of the leading coefficient. Remember, in this polynomial, this number right here, that is my constant. And then my leading coefficient in this case would be an imaginary 1. So this is my leading coefficient. Okay, so what are the factors of my constant? Well, what numbers multiply out to -8? Well, I know that positive or -1, positive or -2, positive or -4, and positive or -8 are numbers that multiply out to -8. And then what are numbers that multiply to 1? Well, positive or -1. So now, what are my actual possible rational zeros? Well, positive or -1 divided by positive or -1, that's just equivalent to positive or -1, positive or -2, positive or -4, and positive or -8. Okay, so those are all my possible rational zeros of this polynomial. Now you need to figure out which one of these possible zeros is a factor. And how do we do that? Well, you have to use the factor theorem that we used last time, where we substitute one of these numbers into x there, and there. And if it gives me an output of 0, then I know it's a factor. So we're going to go ahead and substitute in first is a 1. Let's try a positive 1. So what is f of 1? Well, that's going to be equivalent to 1 cubed plus 3 times 1 squared minus 6 times 1 minus 8. If you go ahead and work this out by hand or type it into Desmos or into a calculator, 1 cubed is 1, plus 3 times 1 is 1, plus times 3 is a positive 3, minus 6 minus 8. That will simplify down to 4 minus 6 minus 8, which is negative 10, right? No, I don't know, a number. However, this number is not equal to 0, so obviously we know that 1 is not a possible factor to this polynomial. So let's go ahead and let's try my second one. So a negative 1. My second possible factor, rational zero here. So this would be negative 1 cubed plus 3 times negative 1 squared minus 6 times negative 1 minus 8. Let's go ahead and simplify this down. This will give us negative 1 plus 3 plus 6 minus 8. Negative 1 plus 3 is equal to 2. And then plus 6 minus 8 is equal to 8 minus 8, which equals to 0. So this one checks out. So negative 1, we know, is indeed a factor to this atop polynomial. So x equals negative 1 is definitely one of my factors to this polynomial. So what I'm going to now go ahead and do is I'm going to use synthetic division to figure out the second part of my factorization. So I'm going to go ahead and put a negative 1 on the outside of my synthetic division. I'm going to fill in my coefficients here, which are 1, 3, negative 6, negative 8. Drop down my 1. Negative 1 times 1 is negative 1. 3 plus negative 1 is 2. Negative 1 times 2 is negative 2. Negative 6 minus 2 is negative 8. Negative 1 times negative 8 is a positive 8. This times this is 0. Obviously, we were expecting a 0. We already knew that negative 1 was indeed a factor. So now to go ahead and rewrite this synthetic division, I would be left with x squared plus 2x minus 8. Okay, so what I'm now going to go ahead and do is, remember, our goal is to solve this. In order to solve this polynomial, which I'm going to go ahead and rewrite down here, we know that x cubed plus 3x squared minus 6x minus 8, let's call that function f of x, that is going to be equivalent to... how would I rewrite this one as a factor? Well, that'll be x plus 1. So I'll have x plus 1 times my other polynomial over here, which was x squared plus 2x minus 8. And then you need to ask yourself, how can I factor down that second polynomial even more? You can always check to see if the x method works. If it doesn't, then you have to go to the quadratic formula. Think about it here. Are there two numbers that multiply to negative 8 and add up to 2? There indeed is. It is a positive 4 and a negative 2. So my two factors would be x plus 4 and x minus 2. You want to go ahead and set these equal to 0 to solve them, because we're actually solving for the zeros here. So what are my three values of x here? Well, x could be equal to negative 1, negative 4, or positive 2. And these are my zeros of the polynomial. Okay, so this is us factoring and, not factoring, using the factor theorem and using synthetic division to find the zeros of this polynomial. And remember, these are the points where this polynomial is going to cross the x-axis. I can always go on to Desmos to show you this. So the polynomial that was given to us was x cubed plus 3x squared minus 6x, minus 8. And then it's this crazy looking polynomial, right? However, what are the 3 points where this polynomial crossed the x-axis? Well, -4, -1, and a +2. And that is indeed what we got right there. Okay, so this is us solving these polynomials now, finding the zeros, using the rational zero theorem to figure out the possible zeros, and then using the factor theorem to figure out, well, which one of these possible ones is an actual factor. Once you have one of the factors, then you can use synthetic to figure out the second part of the polynomial factored. And then once it's in this form, and you'll always end up with like some type of quadratic here. You can use the X method, you can use the quadratic formula. In other cases, you'll notice that sometimes we'll have to use factoring by grouping or other methods to set it equal to 0 and then solve for the zeros. Okay, so that was kind of an easy example. We can go ahead and try one more just to show you guys, have you guys watch me do it one more time. And then I'll do one, I'll probably have 3 examples on these sets of notes. They might be a little bit long, so bear with me. Let's try another one. Let's do this one. F of x is equal to x to the 4th plus 3x cubed minus 7x squared minus 27x minus 18. Okay, I need you to find the zeros of this polynomial. Find where this polynomial crossed the x-axis. So we have to first figure out what is a potential factor to this. So let's list out first all the possible factors, the possible rational factors using our rational zero theorem. So we have to first list out what are the factors of our constant and then divide those by the possible factors of our leading coefficient, which in this case is 1 again. So what are the possible factors of -18? Well, we know that there's a positive or -1, a positive or -2, and you always have to include the positive and the negative version here. Whether this number is positive or negative at the end, you always have to do the positive and the negative version of the factor, because remember, you can always take a negative and multiply it to get a positive, or you can take a negative and a positive to give you a negative. So carrying on with our factors, we have 1, we have 2, we have positive or -3, we have positive or -6, we have positive or -9, and then we have positive or -18. Remember, these are all the numbers I can multiply to give us 18. Now, what are the possible numbers that give us our leading coefficient? Well, our leading coefficient is 1, so it would just be positive or -1. Now you have to go ahead and divide these out. 1 divided by 1, well, that's just 1. 2 divided by 1, that's just 2. 3 divided by 1, that's just 3. So like in this case, because our leading coefficient is 1, there's not really anything that needs to be divided it by. So our possible rational zeros here are just positive or -1, positive or -2, positive or -3, positive or -6, positive or -9, and positive or -18. Now you need to go ahead and figure out which one of these possible ones is indeed a factor by using our factor theorem. So I always like to start with the 1. You can start anywhere you like. Let's try f of 1 first. What is f of 1 equal to? Well, f of 1 would be equal to 1 to the 4th plus 3 times 1 cubed minus 7 times 1 squared minus 27 times 1 minus 18, blah, 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 blah. I'm going to tell you right now, this one doesn't work. I don't want to do the math for it. The one that ends up working for this one, I hope you guys know how to solve this. So literally just type it onto your calculator or just work it out by hand. The one that ends up working for this one is, again, -1. F of -1 is our winner here. You end up getting -1 to the 4th plus 3 times -1 cubed minus 7 times -1 squared minus 27 times -1 minus 18. This is our winner that ends up, once you do the simplification, it gives you 0. So you know that x is equal to -1 is a factor of this polynomial. So now that you know that -1 is 0 to this polynomial, you're going to put -1 on the outside of your synthetic division. You're going to fill in your coefficients, which in this case are 1, 3, -7, -27, and -18. You do your synthetic division. Remember, you're able to do synthetic division for these not long because these are linear factors, right? This one would be equivalent to x plus 1 as a, like in linear polynomial form. So these have a coefficient of 1 and a degree of 1, so you can use synthetic. This gives you -1, this gives you 2, this gives you -2, this gives you -9, this gives you +9, this gives you -18, and then this gives you +18, and this gives you 0, as you were expecting. So now you can go ahead and rewrite this polynomial. Obviously, remember, this one started off with to the 4th power, so when I do my synthetic, this first term is actually a cubed term. So this would be plus 2x squared minus 9x minus 18. Okay, so now to continue the factorization of this so that you can find the zeros, it would be f of x is going to be equal to, well, our original linear factor, which was x plus 1, times our synthetic division polynomial, which was x cubed plus 2x squared minus 9x minus 18. And like, for example, this one, you should notice that this polynomial is not a quadratic. So you cannot just use the x method, or you cannot use the quadratic formula. Instead, you should realize here that this polynomial can be factored using factoring by grouping, where I can, if you need a little refresher, factoring by grouping here, you can separate the 4 terms in 2 groups where you find what is the common GCF, and then you just rewrite the common one time, and then you write the leftovers as a term. So like going back here, you can treat this as one group and then this as a second group. So what can you factor out from that first group? Well, you can factor out an x squared, and then you would be left with x plus 2. And then in the second one, you can factor out a -9, and then you would be left with an x plus 2. So when you rewrite this, this would be x plus 1 times x plus 2 times x squared minus 9. And now at this point, you already, you want to set them equal to 0. You can figure out some of the x's, like this first one, you know, is x is equal to -1. You know that the second one is -2. Now on this one, again, it's a quadratic, and you should notice that it's a difference of squares. This can actually still be factored, where I can put an x and then a +3 and a -3 equal to 0. So this one ends up being -1, -2, and then a positive or a -3. Okay, and you should be noticing here, how many zeros did I get here? 1, 2, 3, 4 zeros. How many? And then what was my degree? 4. Over here, how many zeros did I get? 1, 2, 3. And what was my degree? 3. Remember, the degree tells you the number of real zeros that you'll have in a polynomial. So in this case, you expect 4 real zeros since your degree of your polynomial is 4. Again, you can always verify this by going onto Desmos and graphing it. In this case, the polynomial was x to the 4th plus 3x cubed minus 7x squared minus 27x minus 18. We get this crazy looking polynomial here that we see crosses the x-axis at 4 points. More specifically, -3, -2, -1, and +3, which if you look back here, those are the exact zeros that we got. So we have found the zeros of this polynomial. Okay, we've solved it. I said I did want to do one more example with you guys, so I am going to very quickly locate it for you all. It's essentially whenever because I need you guys to understand that you could get irrational zeros where they're not pretty whole numbers like this, and you can also get complex zeros, the ones that have the I in it, like when we were working with the quadratics that had the negative number under the square root. Just because you get like a -4 under the square root, that means that your root would be positive or -2i. Okay, so in polynomials, you could get these types of roots, which we call complex. And then remember, sometimes like in the quadratic formula, we would get like roots that were looking something a little bit more like -4 plus or minus the square root of 21. Those you could also get, which we would call irrational roots. So polynomials do have these as well, similarly with quadratics, because remember, quadratics are just a type of polynomial. So these are what we call like rational roots because they're nice, clean, whole numbers, but they do also get complex and irrational roots. It just means that your algebra at the end doesn't turn so nice and pretty. So I will go through one of those with you guys. I don't think I'm going to have time for two because I feel like if I make it any longer, you guys will zone out. So maybe I'll give you guys a complex root one just so that you can kind of see what that looks like. I think the irrational ones, you guys should be fine. I can like show you guys an example of an irrational root in class if you'd like. Okay. It's just when you do your factorization at the end, like at this part, it's just not going to end up being nice, clean numbers. I'm trying to look for a complex root one. Sorry, guys. 1 second. Okay, here we go. So last example, and I'm going to give you guys one with the complex root. It's just going to look a little bit more complex, but it's the same idea. So let's say that I give you the polynomial f of x is equal to 2x squared minus... Whoa, that looks weird. Sorry, wrong one. 2x, why does it say 2x squared? Sorry guys, 1 second. 2x, I think that's supposed to be a cubed. 2x cubed, my apologies. Minus 5x squared plus 8x minus 20. Okay, wait, I need to check this because it's bothering me now. On this other paper, it has it as squared. 1 second, guys. Okay, yeah, there you go. 2x cubed minus 5x squared plus 8x minus 20. All right, so let's go ahead and solve this one. Let's find the zeros. So we have to first use our rational zero theorem to find the possible zeros. Remember the possibles, you do P over Q, which is equivalent to the factors of negative 20 divided by the factors of a positive 2. So what are the factors of negative 20? Well, it's positive or negative 1, positive or negative 2, positive or negative 4, positive or negative 5, positive or negative 10, and then positive or negative 20. All of those over the factors of Q, which would be positive or negative 1 and positive or negative 2. So obviously, in this case, you're going to have the set of this over this, 2 over 1, 4 over 1, 5 over 1, 10 over 1, and 20 over 1, which are just all the same numbers. So you would have positive or negative 1, positive or negative 2, positive or negative 4, positive or negative 5, positive or negative 10, positive or negative 20. And then on the second set, though, sorry. On the second set, you should notice that you have positive or negative 1 over a positive or negative 2. So that creates another possible solution, which would be 1/2. And then you have 2 over 2, which is just 1. It's already written out over here, so I don't actually need to write that. 4 over 2, which is 2, I don't need to write that. 5 over 2 is another possible one, so I do need to include 5 over 2. 10 over 2 is 5. That's already written. I don't need to include that. And then 20 over 2 is 10, which is already included. So these would be my last final possible set of zeros to this polynomial. So now to figure out which is an actual factor, you need to substitute them into your original polynomial and see which one gives you an output of 0. For time purposes, I am going to go ahead and tell you guys which one the answer works out being. It is actually f of 5 over 2. Okay, f of 5 over 2 is the one that gives you 0. But yeah, you would have had to had gone through all of these by hand to get that. To be honest, I'm going to be completely straightforward. I don't know if there's a shortcut, and I don't think there is. When I was in high school, it was always just like, use your calculators. If there is a shortcut, I'll ask around and I'll let you guys know. But to my understanding, all I know is that, yes, you have to just substitute every single one of them in and see which one gives you 0. Okay, so now that we know 5 over 2 is our one of our factors, obviously you write that as x is equal to minus 5 over 2. So let's go ahead and use our synthetic division. So 5 over 2 is going to go on the outside. My coefficients are 2, negative 5, 8, and negative 20. I'm going to go ahead and drop down my 2 first. So what is 5 over 2 times 2? Well, denominator and numerator eliminate out, and I'm left with just 5. This brings down a 0. This brings up a 0. This brings down an 8. Over here, this is like 5 over 2 times 8 over 1. These eliminate out to a 4, so it's just 20 over 1, which is just 20. Obviously, it simplifies down to 0, which we were expecting, okay? So to rewrite this polynomial, it would be, I started off with a cubed, so this would be 2x squared plus 0x, obviously, and then just plus 8. Again, what happened there was this one should be plus 0x plus 8, which is just simplified down to 2x squared plus 8. Okay, so what are my factors here? Well, we know that my first one is f of x is equal to x minus 5 over 2. And then your other one is a 2x squared plus 8. So this is where you're going to get some complex numbers. So please do not think you're doing anything wrong. This one in the front gives you, obviously, this, when you set them equal to 0, the first one obviously gives you your 5 over 2. However, this second one, when you set 2x squared plus 8 equal to 0, there's a couple things that you can do here. First, you should realize that there is a factor of 2 that you can take out. So you're left with x squared plus 4 is equal to 0. Once you set this to solve equal to 0, you can try to use your X method. So sorry, I didn't mean to write that. Like for this inside part, you can try to use your X method. You can try to use the quadratic formula, that X is equal to negative B plus or minus square root of blah, blah, blah. But there's another method to solving quadratics, which I'm not too sure. I don't remember if we went over it, but it's essentially solving by taking square roots. And what you should notice here is that you can do x squared plus 4 equal to 0. Subtract 4 to both sides. This eliminates out. You get x squared is equal to negative 4. And then you can solve this by taking a square root to both sides of this equation. On the left-hand side, the square root and the squared eliminate out, and you're left with just x is equal to, well, what is the square root of negative 4? You guys know it is positive or negative 2i. So in this case, my three roots here are x is equal to a positive 5 over 2 and then a positive or negative 2i. Okay? And again, we got three roots, 1, 2, 3, and we did have a degree of 3, so we know that we have our 3 actual zeros here. Okay, and this is an example where you get a complex root. You can get real roots, you can get, rational roots, you can get the irrational ones, which I kind of showed you guys. If you guys want an in-class example, let me know, and then you can also get complex roots. Okay, so this is how you solve polynomials using the rational zero theorem, some factor theorem, and a little bit of synthetic. And remember, these give you the zeros, or what we call like the roots or the x-intercepts, however you want to refer to them, of these crazy looking polynomials that we're working with now. Okay, I know this was a long one. If you have any questions, let me know. If not, then good luck on your guys' class.